My name is Werner Kirsch. We just swapped the sessions we are chairing. And the first speaker this afternoon is Illya Gruzberg. He will speak about quantum Hall transitions and conformal restriction.
So I wish to thank the organizers for inviting me here and giving opportunity to speak. So this is a work that has been going on for some time, involving Eldad Bettelheim from Jerusalem and Andreas Ludwig from Santa Barbara. So after several years of work, it's finally out on the archive. So let me start slowly by explaining what the setting is. So if you think about what classical Hall effect is about, it's just you take a thin sheet of metal or any conductor, you place it in a perpendicular magnetic field, push the current one way, and measure the voltage across this sample in the perpendicular direction. What you measure is called the Hall voltage, and if you divide it by the current, this is what's called the Hall resistance. And the classical considerations easily lead to a formula which tells you that this Hall resistance should be proportional to the magnetic field. Now, if you take a thin, specially prepared two-dimensional electron gas, cool it to very low temperatures, and put it in a very strong magnetic field, at very low fields, you do see this linear behavior, but eventually it is replaced by these striking steps with very sharply quantized features, plateaus, separated by these transition regions. And the quantization here is to a very high degree of accuracy. This n is an integer number. Okay, so this is what I'm going to speak about. This is the so-called integer quantum Hall effect. Now, notice that if you look at the same time at the longitudinal resistance along the flow of the current, it is 0 where we have the plateaus and only has spikes between the plateaus. So in a sense, this transition between the plateaus is a transition between two insulating phases. So there's one insulating phase over here with 0 resistance and conductivity, if you want, and this one is another insulating phase, and there's a transition between them that is an example of an Anderson transition. Okay, so while in mathematics it's, people try to prove theorems about existence of either one phase or the other phase, I'm more interested in the critical properties near the transition, which is by order of magnitude harder probably than anything else here, right? So this is largely unsolved problem even from the physics point of view, right? We don't have answers or predictions, how mathematicians call it these days. So, but once we consider integer quantum Hall, one of the basic simple models for this is just this Schrödinger operator in the magnetic field with a random potential. So that's a typical example of what we want to do. If you remove the disorder, then the problem is simple. We know that the energy spectrum is discrete and it falls into Landau levels. And then disorder broadens these Landau levels into bands. And what we believe is that practically so more or less any energy between this, in the middle of this band, so between the bands corresponds to a localized state, and the only extended states exist exactly where this initial clean Landau level existed before. So then upon varying the chemical potential or the magnetic field, we can sweep the Fermi energy across such a extended state, and we have a transition then. Now notice this one dashed line over here that shows the typical extent of a state at a given energy, and that diverges at these extended states. And again, the belief is that this is describing this behavior. So this localization length diverges as a power law as we approach these special critical energies. So this is a typical example of a critical phenomenon. So in this case, it's an Anderson transition, a quantum phase transition driven by disorder. And similar to the continuous phase transitions in classical statistical mechanics, we expect that various observables, various measurable quantities, will exhibit some scaling behavior, like transfer coefficients could be described by some scaling functions. And this is an experimental situation where, for example, you can look at the transition at different temperatures. So different traces show different temperatures. They intersect at one single point, and you can look at the slope of this step at this point and plot it as a function of temperature. And you see the log-log plot of this quantity shows a straight line, so which means that the slope of this transition diverges as a power law as you approach the zero temperature. So this is a typical example of a critical phenomenon. So anyway, so this is just an overview. I'm not going to talk about much about this. This new? Yeah. Experimentally, it's about 2.34. Numerically, it's been changing over years. So now it's 2.6. Okay. Well, for a model, for a specific model of this phenomenon. Okay. So this is, one has to distinguish things. So for the experiments, the interactions are very important. The model I'm going to be describing and working with is a non-interacting model. So it's somehow it's disconnected, but nevertheless. So as in any second-order phase transition, we're looking for ways of finding critical exponents and scaling functions and correlation functions at the transition, right? So I should say that for this particular transition, there's no generally acceptable analytical description of this critical region so far, even though there are very intriguing proposals by Martin and Celic and Leclerc and others. So, but there are some problems with them, so I'm not going to talk much about them. So we expect this transition to have conformal invariance. At this critical point, we should have conformally invariant properties. This is similar to, again, Anderson's two-dimensional transitions in statistical mechanics. And there are plenty of numerical results that confirm this intuition that we should have conformal invariance. Okay, so what we are going to do. So instead of trying to develop a field theory description of this thing, as would be natural for any person with a background in stat mech, we will use new ideas which appeared recently as alternatives to description using conformal field theory, namely those of stochastic conformal geometry, namely Schramm-Loebner evolutions and conformal restriction. So I will not have time to explain SLE. I will say more about conformal restriction, which seems to be more relevant for this problem. So these ideas have appeared in the context of classical non-random statistical mechanical systems, and we are dealing, on the other hand, with a quantum and disordered system. So it seems to be very far away from the natural habitat of this SLE. Nevertheless, we can show that they can be applied here, and this is one of the main sort of points to take away from this talk. Now, so let me briefly summarize what we can do using this approach. So first of all, to have anything concrete at all to say, we have to be very specific. So we are focusing on a very particular model, very well-defined model of the integer quantum Hall transition, the so-called Choker-Konnigsen network model, which I will describe. Secondly, within this model, we focus on a particular class of observables introduced by Martin and co-authors in the late 90s called point contact conductances. Again, I will explain what that is. So apparently, what the first result that is somewhat unusual is that the average point contact conductance in this system maps to a classical problem. So we start with a quantum phase coherent random problem, define this observable, average it over the disorder, and then the result can be viewed as a classical statistical mechanics problem. Okay. So then we establish what's called restriction property. Again, I will talk about what that is. And this, together with the assumption of conformal invariance in the continuum limit, allows to use this recently developed conformal restriction theory to obtain average point contact conductances in systems with various boundary conditions. So here's the Choker-Konnigsen network model. The background is that you can describe the motion of electron in strong magnetic field and a smooth random potential in a semi-classical way, where electrons essentially drift along equipotential lines in this random potential, and then they can tunnel across the saddle points. And classically, this looks like a percolation transition upon changing the occupation number here, right? But quantum mechanically, the tunneling across the saddle points changes the picture. And Choker and Coddington decided to simplify this spatially random setting to a regular geometry where the nodes of this network are supposed to represent the saddle points in this potential. And they're described by some kind of a sketching matrix, each of them, which connects the incoming fluxes and outgoing fluxes. Okay, so this model is specifically designed to describe transfer properties where you can insert the current. So you inject the current from one of the links that are connected to the leads, and you can extract it from the other side and see how much of the current is transmitted. So that's exactly the conductance that I'm going to talk about. Okay, so now slightly more details about the network model. So the state of the system is described by a collection of complex numbers associated with links. So this NL is the number of links. So this is our space of states. And the evolution of the system is described by a in discrete time. So it's described by a sketching matrix, large UN, such that it has matrix elements connecting these numbers on two neighboring links. And for a single node, it's just a 2 by 2 unitary matrix, okay, with randomness specified later. So in fact, I guess I'll specify it right now. So this U2 sketching matrix is usually represented by having some random phases associated with links coming to the node, and some non-random part that simply tells you what's the probability of turning right and left at a given node. Okay. Now, the extreme limits show that this is sort of similar to what happens at the quantum Hall transition, as you believe. So if you take t equals 0, and everything turns to the right with probability 1, and you see these localized states in the bulk which are not connected to the leads at all. So this is an insulator. And on the other hand, if you turn if everything turns to the left, then again the states in the bulk are localized, but along the edges we have edge states that propagate and allow for transmission of current from left to right. Okay, and by symmetry we know the existence of the critical point exactly at a specific value of t, when probabilities of turning right and left are equal. Okay, so now this recent ideas of conformal geometry always work in a finite system. This is very crucial to use conformal maps, because conformal maps are not globally defined. They have to be defined always in a domain. So for that reason, we need to consider boundary conditions. And for this model, there are natural boundary conditions that can be distinguished between the reflecting ones, where the flux coming to the boundary is just bouncing off with probability 1. And even these two can be distinguished between the right moving and left moving boundaries. And then you can also imagine having a metallic lead attached to your system where electrons approaching this metallic lead can escape into it and never come back to the system again. So this is what we call absorbing boundary. And you can actually put them together and mix them in various ways. Okay, so now let me define what the point contact conductance is. So first of all, so suppose I inject some current over here. So phrased as a scattering problem, I should be able to answer the question of what's the scattering amplitude for the electron to go from here to here. And you can easily find that by looking at, let's say, a representation of the resolvent of the evolution operator in terms of paths, that this is simply sum over all possible paths that connect these two links. And along each path, you simply multiply the matrix elements of the scattering matrices. Okay? So notice that in this representation, what can happen is that the particular path can circle around the plaquette, and in principle it can circle around the plaquette as many times as it wants. So the sum over here is infinite, even for a finite discrete system. Okay, so that seems like a rather complicated representation. So the point contact conductance is simply the absolute value square of this amplitude. Okay. And what we consider, this is the first result that I will explain a little bit more, is that we consider the averaging over the disordered phases. So over here, I didn't mention, so disorder is assumed to be associated with these phases on the links, and they're assumed to be uniformly distributed from 0 to 2 pi. So once we take this quantity and average it over the disorder, we can, so in this representation, as you can see, This would be a double sum over paths. But we can rewrite it in a particular way, which becomes a sum over objects, geometric objects that we call pictures. And each contribution here is a positive quantity. So unlike the original thing, if you write this double sum for this amplitude absolute value squared, the terms come into complex conjugate pairs, but there's no guarantee that we'll get a sum of positive quantities, right? So on the other hand, we can write it as a sum of positive quantities after a certain resummation. Okay?
So what's responsible for the fact that that's positive?
Which one? These ones? Yeah. Well, it's the same, more or less the same idea that you have always a pairing between the forward and backward going paths, which are complex conjugate to each other, right? And then they eventually become give you a positive contribution. It's slightly more complicated than that, and I'll explain it right now. But just before I do that, let me essentially tell you that once you have this description, you can view these pictures as the basic objects of your statistical mechanics, such that each of them has a weight. So we have some kind of Gibbs distribution. You can study it using traditional stat-mech approaches. Right? So that's very hopeful. And I should also point out that this representation in terms of pictures with positive weights valid everywhere in the phase diagram, not only at the critical point, but everywhere. And more general conductances, such as between two macroscopic leads, can be obtained from these objects by just summing over the initial and final links.
Is it longitudinal or also off diagonal?
Anything. I mean,
diagonal is not obliged to be positive.
No, so sorry. What you're talking about? What?
All ordinary and whole.
So conductances or conductivity?
Whole. I would say for whole you don't have to be positive. It can be any sign.
Well, it depends. So I mean, if you think, let's say, for the tensor sigma xy and sigma yx, they're of opposite signs, right? Sigma xy and sigma yx are negative of each other.
Yeah.
So one of them is positive. So let's think of this is the one that is positive. You see, it's defined as something manifestly positive, right? So that's, again, just for the comment for experts. So this is a variant of the Landauer formula, and there are variants of Landauer formula for the whole transport coefficients. Slightly more complicated, but it doesn't matter. Okay, so this is what pictures are. Let me tell you. So initially we were working with Feynman paths, and then what we can do, we can sort of bunch together all the paths that follow the same set of links, but not necessarily in the same order. Okay, so this is an example of the simplest example of figure 8, where you have two paths, and they go through the same set of links, the same number of times, but in a different order. Okay, and so if we forget the order in which they follow these links, this is what you are left with. We call it a picture. And after bunching together such paths, we can show that pictures interfere in this absolute value squared thing, that they only, the advanced and retarded pictures should really be the same. And after doing that, you will see that this weight of a picture is a square of a real number. Okay, so that's the way we see it. It's a positive quantity. In the simplest case, when we have a critical system, this S of p is given by the length of the paths that contributes to the picture here. And here we have some numbers of minus signs which come from the sort of, in this representation, okay, so so mathematically they come from the existence of this negative matrix element of the sketching matrix. But you can have them geometrically represented by local maxima of this path over here. So two different paths have different numbers of local maxima. And so these minus signs are not necessarily the same. These numbers are not necessarily the same parity for a given path, two given paths. Right? Yeah.
But what about the interference of the path from different pictures?
They don't interfere. They just give you 0, right? Because the phases would then have, you know, n1 here and n2 here. After integrating over them, you'll get 0. Okay, so we do know how to enumerate all the paths that lead to the same picture. That's a rather straightforward graph theoretical problem. But with this minus signs, this is much harder, and we don't know what to do with these weights microscopically. In principle, there's a hope that one can probably solve this problem at some point. Exactly. But we don't do that. We don't know yet how to do that. So we try a different approach. We can try to go directly to the continuum using restriction property. Okay, so this is in the spirit of the how SLE deals with critical stat-max systems in two dimensions. So this is a purely geometric description of classical conformal variant two-dimensional systems, which is in some sense complementary to the conformal field theory description. And instead of focusing on local objects, local correlation functions, it actually looks directly at some geometric structures that appear in a critical system, be it clusters or cluster boundaries, and looks at their fractal and probabilistic properties. And it's a beautiful theory that is very famous, and actually happens to be not only a purely abstract mathematical tool, but a powerful analytical and computational tool. You can actually extract lots of results from it. Well, unfortunately, SLE as such doesn't seem to apply to our case, simply because the pictures that we introduce are neither clusters of spins, nor the boundaries, nor loops of any kind in the local model. Moreover, SLE with this special parameter kappa corresponds to the central conformal field theory with the central charge, which is given by this formula. And for technical reasons related to supersymmetry, which is applicable in these cases, we believe that conformal field theories for Anderson transitions in two dimensions should all have central charge equals 0. And so this only leaves us with two values of kappa for SLE. And this is definitely not enough to describe the variety of conformally invariant critical points in two dimensions.
And this is 0 because the density of states...
No. This is 0 because the partition function is always 1 for any disorder realization.
Okay.
Yeah, right. Okay, and so what we argue is that it's not SLE as such that applies to our case, but slightly refined variant of it, or a related construction called conformal restriction. So let me explain what that is. So I'll spend some time talking about the conformal restriction. So here's the story, invented essentially by Lawler, Schramm, and Werner. So one should start thinking about some finite domain with two marked boundary points, A and B, and an ensemble of curves in this domain. So suppose you have some measure on these curves. Okay, now suppose we have some set A which is attached to the boundary of this initial domain D. One can be precise about it, such that it doesn't touch A or B over here. Okay, and then you can define a measure on the curves that live in the subdomain in two different ways. One natural way is to say that we only restrict all the curves to be in the domain already to start with. So we only keep the curves that are already in the subdomain and throw away the ones that intersect the domain A. Okay, and we renormalize it to get a probability measure again. And the second way to do this is to conformally map the original bigger domain to the smaller domain and to assign the probabilities accordingly. Okay? So this is simply a conformal transport of the measure. So nobody tells you that these things may coincide. But however, this is one of the main results of this paper, is that there are such measures that the two ways of doing it give you the same probability measure in the end. Okay? Not only they prove this existence of such things, they classified them all. They showed that there's a single parameter family of such measures, and this single parameter has an important role, which I will introduce later. Before I do that, let me mention that there are two variants of this thing, actually. One is called one-sided restriction, where we only allow this extra set to be attached on one side of the curve. And the other is two-sided restriction, where this set can be disconnected and placed on different sides of the boundaries. Okay. So it's known that if you're in this situation, then the only measure on curves that really satisfy this thing is produced by SLE 8/3. So it's the same as self-avoiding walks in the continuum limit. So this is not, again, this is just too little for us to work with. And luckily, the restriction theory applies to more general sets, not necessarily curves. So they can generally look like sausages stringed together so that they are fatter than curves, okay? And one example that is prototypical in this case is just a Brownian excursion between these 2 points. So you start a Brownian walker from here to here, and obviously there are all kinds of loops and holes in it. But once you fill in all these holes, you get a compact set of this type, and that satisfies the two-sided restriction property. And once you do this filling in, it's actually sufficient to look at the boundaries of these sets, because if you ask yourself, what's the probability that the set intersects this A over here? It's the same as to ask whether its boundary intersects A or not. It's literally one-to-one correspondence, right? So, and it's been shown by these guys that the boundaries of such sets are variants of SLE, closely related to the original SLE, called SLE 8/3, rho. So there's one extra parameter rho, a free parameter that ranges over a whole interval of values, and that allows to distinguish different types of restriction measures. Okay.
What does the rho represent again? I mean, the 8/3 is the kappa, which has.
Yes, 8/3 is the kappa, and rho is another one, which sort of essentially measures the thickness of these guys, right? So when kappa is 0, this is a curve. When kappa is bigger than 0, sorry, rho. When rho is 0, this is SLE. When rho is bigger than 0, it's something bigger than a curve.
And does it have to do with the Bessel process or something?
Yes, it does. Yes, okay. It does. Mm-hmm. But again, I'm not going to spend too much time on details here. The point is that SLE is a very well-defined stochastic differential equation, and a process that can be studied very precisely. One can write, for particular observables or particular events, one can write differential equations and can be solved. And it actually gives you some explicit answers for various quantities. So it's not just a way of proving existence theorems. So there are some examples. So Brownian excursion is one such thing. The self-avoiding random walk and conditioned percolation halls also the restrictions.
So yeah, this rho defines the equation or the type of noise.
Rho becomes a kind. It's a parameter in the equations that you study. It's related to the. I'll show you in a second what it's related to. Okay. Okay. One thing is that what we call restriction here. It's a very it's a very simple thing. You really start saying, can I define a measure in the subset starting with a measure in the big set? And anything that is intrinsic can with any weights of objects that you look, which are intrinsic, this can be done. Intrinsic means that it's only depending on the shape of the object itself and nothing else. So Brownian excursion is a good example. So the weight of this thing is really related only to its length. It's 4 to the minus the length of this object on a lattice, right? So that doesn't really care whether it lives in the upper half plane or a circle. Right? So for that matter, it doesn't really, this is a very intrinsic weight. So for intrinsic weights, we can always define what restriction means. The conformal variance is much more tricky, and it would have to be proven really to be applied, but we assume it here. So it's a very natural assumption. Moreover, it's convenient to use not probability measures, but finite measures with some total weight. Okay, and this total weight we call the partition function of this particular measure. That can be defined in a way where you start with some standard domain and assume that the weight of the objects there is 1, and then you use conformal invariance to map it to any other domain, and then the corresponding weight doesn't have, or use restriction to define it in other domains, and then the weight will be bigger or smaller. It will be something that is finite, but depends on the domain D and the points A and B. Okay, so now what are the properties of the restriction measures? So the main property is that you can explicitly write, for example, this object. You can ask, so given the restriction measure, what's the probability that the particular, I should have written K here, that this set K stays in the subdomain, does not go into this A. The answer is given explicitly by this formula, where F is a conformal map from the subdomain to the big domain that preserves the boundary points. And the H here is a parameter that is related to that rho. In that SLE kappa rho is a boundary of this guy, and rho has a relation to this H, which is called the restriction exponent. So this is restriction exponents are known for many cases, but from the point of view of a physicist, one can actually slightly extend this result to these unnormalized partition functions, and then one can see that they transform when you go from one domain to another by multiplication by this factor here. So if you look at this, any person familiar with the conformal field theory will immediately say, aha, this is a two-point function of primary fields, what's called, right? So, and this H is the dimension of the primary field that is being studied here. Okay. So, in principle, one can study more complicated objects where there are more than two marked points on the boundary. For example, you can have these different boundary conditions merging at one point, and in this case, the object will depend on more points, but they still will be constrained a lot by the requirement of restriction and conformal invariance, and they satisfy a whole bunch of differential equations that can be written explicitly. Okay, now, so first of all, I want to mention here that the weights of the pictures that we have introduced are intrinsic. They are not local. They're not. They know about the whole thing, but they are intrinsic in the sense that they don't care about whether the picture is drawn in one domain or a different domain. Okay. They are also satisfy restriction property with respect to absorbing boundaries. Namely, this is one of the crucial points. So if you have an absorbing boundary where electron can escape into the lead, and you move it in, then obviously the pictures that used to contribute to the conductance keep contributing to the conductance only if they do not intersect this new boundary. If they do intersect this new boundary, that means that along the Feynman path that was contributing to this picture, electron will necessarily escape into the lead. So those have to be thrown away. So it's automatically what we call restriction property. And if we assume conformal invariance, then we can use conformal restriction theory. And okay, I guess this used to be an overbar. So the average point conductance is simply, by the formula that I was showing you before, it's a sum of weights of the pictures. This is simply the two-point function of this. This is simply the partition function of this probability measure, this partition of this restriction measure. So this relation, which is established by these two, one is a demonstrable property, the other is an assumption. This is a true statement which is very powerful. It immediately tells you the following statement, that the current insertions that actually create these pictures are primary operators in the conformal field theory. And those can be, once you have this notion, once you have this information at hand, you can immediately write correlation functions based simply on this statement alone. Right? The global conformal invariance in this case uniquely defines 2-point and 3-point functions. Before you write these functions, though, you need to know dimensions of these operators. And from the transformation properties of these guys, we know that this restriction exponent is the dimension that we want to know. So these scaling dimensions we can determine in some cases analytically. In some cases, they are not known and have to be found numerically. But once you assume that you do know the scaling dimensions, these objects and the generalizations thereof to higher point functions can be written explicitly as analytic functions of positions of points. So let me show you what we can do with these things. So first of all, some dimensions. So we can argue that if you inject the current at the absorbing boundary, then the dimension is exactly 1. And it's simply related to the conservation law of the current. We can have these dimensions are not so easily obtainable. These are not known explicitly, but known numerically. This one is an exotic guy where you inject the current through the sort of a shift in the boundary. So it cannot escape anywhere backwards, so it has to be extracted somewhere, meaning that the correlation function will not decay, and so essentially it's a zero-dimensional operator. Well, anyway, so again, there are many variants of these guys, and most of them for the Choker-Connington network model are not known analytically. But they're known numerically, but some of them we do have expressions in terms of explicit rational numbers here. There are variants of this thing that I'll mention later for which we know everything analytically. So once we know these dimensions, we can find two-point functions easily, simply as power laws with these exponents. We can find something more exotic. We can imagine studying the point conductance between two absorbing regions, and we insert a small reflecting region here. The point conductance will increase upon the insertion of this small reflecting region, and the change in it will be described by a three-point function, which again is fixed by global conformal invariance here. And we can argue that this is essentially the dimension of the stress energy tensor in this case, so it's exactly equal to 2. The same effect is obtained if you move a small portion of the boundary inwards, and that also serves as an insertion of a stress energy tensor. One can do slightly more exotic things. One can take a finite reflecting boundary, inject the current right at the juxtaposition here, and extract it here. And then one has to do some partial resummation or integration over the intermediate point where the picture takes off from this interval. And that intermediate point is a parameter in a three-point function. So this happens to be a three-point function, again given by this expression here. So you can explicitly integrate this out. Well, in general, for general values of the weights, you would get some complicated hypergeometric function. However, we can also argue that this dimension of this operator here is also equal to 1, simply based on restriction property and nothing else. So once this actually for this value, this thing simplifies a lot and produces in the end something rather manageable of this type, just three-point function of these two operators and a zero-dimensional operator over here. So some of the weights we can. So the point is that Choker-Connington model is a very specific model for a very specific phenomenon. Conformal restriction is much more general than that. And some of the weights of the operators that appear happen to be dependent only on the conformal restriction property and nothing else. So those we call super-universal. They would apply to a whole variety of Anderson critical points. So I summarize them somehow here, and I can elaborate on this if anybody's interested. But one message one final thing that I want to say essentially is that we know that this circle of ideas applies not only to the Choker-Connington model, but to other models of localizations, or other models of localization as well. There's a variant of the Choker-Connington model describing the so-called spin quantum Hall transition, where it's known that the same objects, the mean conductances, map to a problem of classical percolation on square letters. And then the appropriate objects are simply the hulls of these percolation clusters. And these are, as I mentioned, are known to satisfy conformal restriction property in the continuum rigorously. So there's other things called the classical limit or metal in class D. And in this case, in these two cases, in these three cases actually, all the dimensions are known analytically. And so as a conclusion, I want to say that I tried to present a new way of thinking about, a new analytical way of thinking about quantum Hall transition and related Anderson transitions. We would like to analyze more complicated geometries and boundary conditions, where, for example, we have two reflecting segments and two absorbing segments. Knowing this would, in principle, tell you a lot of things. And unfortunately, from the point of view of a conformal field theory, this is a 6-point function. And so to calculate these objects, you need to know more than just the nature of the operators being primary and their dimensions. You need some more complicated conditions on them. There are some ongoing numerical studies that would help us, hopefully, with this. And one can also extend this theory to the conductances defined between the bulk and the boundary, or two bulk points. That would require an extension of the existing conformal restriction theory to these situations, which exists in the heads of some mathematicians but has never been written. One can also try to hope to generalize these objects to go slightly off critical. To see the exponent nu, one has to slightly go away from criticality and then think whether one can generalize this thing. So hopefully this is possible, and the hope is given by the fact that people have introduced the massive variance of SLE. So SLE, which is related to these objects intimately, is known to have massive or non-critical variance. So that's the. So we also hope that this description can be helpful for other Anderson transitions and disordered systems in more general. Thank you.
Thank you, Ilya. Are there questions or comments?
So how many parameters you have in the series? You have this kappa and rho at some point when you. So
Yeah.
you have
So kappa is always 1/3 for these guys, simply because c is equal to 0. As for the rho, there are two rhos. One is related to the right boundary, and the other is related to the left reflecting boundaries. So in fact, there are two different independent parameters that could be varied. And for the quantum Hall transition, for the Chern-Poynton model, they're known only numerically. But for other things, they're fixed, and we know them.
what do you mean other things?
Spin quantum Hall or the class D metal, stuff like this. So for class D, you can have the Hall angle, right, which is different on left and right boundaries. And
Let's say for symplectic class, you also don't know everything. Yeah.
symplectic class, we don't know if this applies at all,
Oh, you
right?
don't.
No, so we hope, but there's no explicit construction, for example, right? In all other cases, I can tell you what these pictures are. So the things that the geometric objects that we're dealing with, for all the cases that we know and we describe in our paper, I can specifically tell you what these objects are.
So you see, for quantum Hall, you believe you have a proof that this applies. It's not a conjecture. On this?
Well, look, no, we don't have a proof. So a proof would be similar to Stas-Smirnov proving that percolation has a continuum conformally invariant limit, right? This would be a proof of that type. But other than Stas-Smirnov, nobody can do it probably. So definitely not me. So
But still, but you say that quantum Hall, so the status of quantum Hall and of symplectic class would be different. Yeah.
absolutely, it would be completely different. So I don't know how to relate it to this anything of that type. I mean, I would have to think separately. We can discuss it later. But again, the focus here was on a discrete model first, and then you try to. Of course, there are network models in all 10 symmetry classes, right? So one can try to start with the network model in this particular class and think about it. But this hasn't been done.
But, as you said in the very beginning, so there were two suggestions about the critical theory made by Zwielica, made by Martin Zimbauer. And those conformal field theory, I guess these dimensions are known for them. So can you disprove
No.
from your new approach, can you disprove those?
No, unfortunately not. So the thing is that those theories are not that simple. They are similar to West-Zumina theories, but they don't really have the current algebra.
So
you-
the dimensions are not known.
The dimensions are not known in those theories,
Okay.
and they're not known for us as well. So I can't compare. I mean,
Okay, so you cannot compare.
no,
with
no,
that.
I cannot compare anything. So, yeah.
I think we have to shift the rest of the discussion to the coffee break. Let's thank the speaker again.